Okay, well, I'd like to thank the organizers for putting together such a fascinating meeting with a mix of topics and exoplanets and solar system. And we've heard all these exciting results of current facilities. And what I'd like to describe a bit now is a basic science case for a future possibility. So it's not a fully designed mission, but something that might be worth considering to identify new exoplanet systems that I think would have some intriguing connections to both the solar system and currently known exoplanet systems. And do I advance with there? Sorry, it's this one? Yeah, press this one. Okay. Okay. Okay, so what you're seeing here is a plot that's a little different from the standard view of the exoplanet population. So what you're seeing here is a way of considering the solar system planets in the context of the exoplanet system, but ordered by they're ordered by the effective temperature of the star. And so in this case, focusing on the rocky planets, and so only the transiting planets with radii of like 2 Earth radii or smaller are plotted as like a generous value for an upper limit considering uncertainties of a rocky planet. And so you're seeing that our own terrestrial planets out here around the sun are, as we've seen in other plots, they're a bit out on their lonesome, and the exoplanet population has not yet extended to fully encompass those are true analogs of our own system. And then what you see are that of all the planets, there are thousands of planets here, and you see that there's this overwhelming majority are often around the planets that are sorry, the stars that are lower effective temperature than our own sun. And so a lot of that has to do with observational reasons that make those easier to detect. And we'll build upon that as a possible future science case. Okay, and one thing you can see here is a scaled version of the radii of the host objects, and you can see how dramatically the drop is as you go from solar type stars. And then even within the M's, I admit this always surprised me that although they're one class of star, they really have such a huge range of properties, and one of those is the radius. So from early M to mid M, the radius is dropping, and then when you get to the late M, it's even smaller still and more comparable to a brown dwarf radius. Okay, so now we've added the habitable zone on the plot, and you can see that for stars, the outer zone, the outer edge of the habitable zone, these come from the Kaparapu estimations. Those can extend to years for stars like F stars, more massive than the sun, hotter temperature. But then if you go down to the lowest mass stars, then rather than years, you're talking about months. So this habitable zone is declining and in its period. And then despite all the intense interest in identifying exoplanets in the habitable zone, you can see that those orange points actually intercepting the purple zone, they're only on the order of 10 or so rocky planets within these expected ranges of the habitable zones scaled to that particular type of star. And then if you investigate the brown dwarf region, that's down here, an extension of the habitable zone, you see that it's no longer like this solid color because there's a bit of a degeneracy between the spectral type does not immediately map unambiguously onto a mass of the object. And so this is like a weighted average of a range of masses that are possible for brown dwarfs. Okay, so then if we look into the if we go ahead here and now look at what our current mission sensitive to and where might there be a scientific opportunity, what you see here relates to why perhaps there are relatively few of these known habitable zone planets. If we add in the sensitivity of what TESS, for example, could observe in transits in terms of its brightness limits, it extends to mid-Ms in a large population. In a few cases, it can get to later M types. And then in terms of the period, the TESS orbit was constructed such that it stared for 20-something days per pointing. And so unfortunately, that time period is actually within less than the inner habitable zone for most stars. There's like a little tiny corner here, where the TESS brightness and period sensitivity would overlap with the habitable zone. So you can see that there are so many planets at the shorter orbital periods, and yet this region here is largely unexplored, because the brightness was to these late M's and all through the L sequence, they're all too faint in the optical for TESS. However, if we were instead to observe in the infrared, they would be much brighter. And you can see that for a similar kind of period, staring time, or actually even shorter, it would be possible to capture sensitivity to this habitable zone. All right. And then there have also been ground-based searches that are targeting similar types of stars, so these late M stars, and then in the Eden and Speculoos, and then also extending into L dwarfs for the Pines survey. And so these have actually provided some really exciting examples of exoplanet systems, particularly this TRAPPIST-1 system, which you see as this string of small planets. And so this gives us an indication that it might be worthwhile to pursue in a larger study these kinds of objects. So the ground-based study that is targeting the L and T dwarfs has as a radius limit more like beyond the rocky planet limit and into the mini Neptune. So something like 2.5 Earth radii is expected to be the limit of the Pine survey. So there's space for searching for a large study of lowest mass objects with these shortest periods. Okay, and so this is where we would like to have a possible discussion about a science mission. And so we decided to call it the Hospitable Planets in Extrasolar System, or HOPES. So we need hopes for new worlds to explore, and that's what this is designed to do. So the idea would be to search these lowest mass targets for the smallest planets. All right. And so you can think about, well, what sort of physical properties might make L dwarfs an intriguing population? And here we see a little brief comparison of some of what has thought to be a complicating factor for the atmospheres of the planets around M stars, that they have high levels of activity throughout their lifetimes, and intense X-rays. By comparison, L dwarfs are detected in X-rays, but typically only at the youngest ages, which is why it was hard to find a plot showing a sequence from M to L, because people don't really plot a lot of their non-detections. However, something that's related is the H-alpha activity. And so this shows you the flux of H-alpha from going from M's on the left on down. You see the large decline in activity as you go to the L dwarfs. And so you might question, well, do L dwarfs have the raw materials for planet formation? And we've seen a lot of talks with exciting ALMA results. And so ALMA has, in fact, imaged disks around L dwarfs. And while perhaps smaller than the comparison solar disk, that's fine, since we're searching for close orbit, low mass planets. We're not looking for a minimum mass solar nebula analog around the brown dwarfs for these kind of systems. Okay, so this gives you an indication of another physical property, that small radius of brown dwarfs that's so advantageous. And this shows you in the plot an example of how the transit depth is massively increasing if you were to search for the same Earth-type object around different spectral types. So Kepler had as a goal searching for solar-type stars, TESS these M's, and then with HOPES, you could have with a much, orders of magnitude larger transit depth, the same type of planet. Okay, so then this is showing how you could get to habitable zones in a hurry. So if you're impatient, you don't have to wait an entire year like you would for a G2 star. For the brown dwarfs, this is showing the inner and outer habitable zone periods. So we're talking about days rather than months or years. And then the transit duration, that's important to setting the observing cadence of a system. That is still manageable on the order of 20 minutes to an hour. So everything is like a rapid payoff with the brown dwarfs. And then fortunately, we can build upon existing results from all-sky surveys. This gives a sense of how bright the targets would be. And the targets are bright enough such that with something like a 20 to 30 centimeter telescope, you have enough photons to be able to observe these stars. Okay, we ran some yield estimations. And so we took simulations or distributions from Kepler in terms of planet size and put in some detectability estimates. Since the peak of the planet period isn't known, we had several cases. And the outcome is that for something on the order of 1,000 targets just in the brown dwarfs, and keep in mind, there are about 1,500 of which we could choose from. This gives you a sense of how we could detect approaching 50 to 100 planets, and then some of them even in the habitable zones. And so then I'll just finish up with, these are some of the basic technical requirements for a mission. You would like to have something like 9-day observation sequences, a test like maybe 3-2 orbit rather than 2-1, a reasonable sized telescope for something like a SMEX mission. And then maybe I should just put up again the summary in case there are any questions. Okay.
Great, thank you very much. Time for one question.
Hi, Zachary Hartman, NASA Ames. So I'm interested in, you're saying that this could be a pathfinder for an HWO extended target sample. But
Oh,
no worries. But are you talking about doing direct imaging on them or?
no.
Okay.
Yeah, so for the HWO, it will do a coronagraphic with a spectacularly sensitive reflected light imaging for Earth-like planets around sun-like stars. But no, this would be for transits. Yeah.
What's this one? What diameter or aperture would you need for a mission like this for the telescope?
Yeah, so if we would like to be able to collect enough photons for signal to noise of something like 5 detection on the transit of an Earth around the faintest target, that would be around 30 centimeters. So if you were willing to focus on the brighter part, then there's a possibility of making a smaller diameter. Yeah.
Once again.